Today in October 27th. Hopefully, guys, I got the sound thing fixed. It seems like it is. So homework 6-3, maybe 6-4 also. We're going to see how much we get done today. So we might also have to do 6-4. Right?
I signed that yesterday.
I know. So it was up yesterday, but I know not everyone did it, and we didn't actually have class to talk about it. So we're going to try to run through 6-3 real fast and see if we can get to 6-4 also. 6-3 was up. It was alive, like able to be done. You weren't supposed to do it, but you could. If you wanted to do it, you could. It was available. You had access to it. So out of curiosity, who did it? Yeah, so it wasn't that hard, right? So that's why we're going to get through this lesson pretty quickly.
Yeah.
So do I have any volunteers to pass out notes? They're all stacked over it, so whoever gets there.
Yeah, I'm good.
Nate wins.
Right?
Alright, so we are looking at units. Now we talked, I forget who it was, looked it up. We talked in scientific notation talking about really, really, really big numbers, like something that had 119 zeros after it. We looked up that there are names for all those, the illions, millions, billions, trillions, quadrillions, quintillions, septillions. It goes crazy. So what we now have is something that may or may not exist. We have a zeptometer. And a zeptometer is apparently smaller than a centimeter, even smaller than a millimeter. So we want to represent this in scientific notation. What we see, as we get smaller and smaller numbers, we're using the negative powers. Now, obviously, some of you have already done your homework, so this is not as, like, discovery moment. Yeah? Let's find out. Well, nanometer, I think, comes pretty closely after millimeter. Pretty sure zepto is smaller than a nanometer. Kind of comparing, like, nanosecond to a zeptosecond. Like, this is fairly certain this is a real thing. So, what are we going to do? How do we determine the power of the 10? How do we determine what my number is? It looks like all of these numbers are all ones. Olivia?
You find what number is on the end.
What do you
Like you look at what number is on the right side.
So what's the rule about the number that we use times 10 to the power?
Wait, never mind.
This number. What I mean,
it has to be bigger than 1 but less than 10.
has to be bigger than 1, less than 10. It essentially has to be a single digit number, decimal, followed by whatever. Now, normally we don't put like tons of decimal places. We'll put 3 or 4. Here, the first number that I have is a 1. It's really the only number that I have. So if you wanted to, you could put 1 with a decimal or even 1.0 if you wanted. Times 10, because we know it's scientific notation. How do we determine our power? We got enough hands up and going to cards. She's in China. Noah, you know, or are you going to pass? Lily?
Yeah, you count the zeros, like you count like the spaces, how many, and it's going to be a negative since it's this.
I agree with what you said. So you can count the amount of spaces. So at first she said count the zeros, but we have to go further than the zeros, so be careful saying that. The other way we could go, put your decimal where we put it in the scientific notation and count back to where it actually lives, where it actually belongs. So if I do that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Negative 21 because we have to shift it to the left. So the negative exponents tells us to move to the left. So your friend is correct. It is 1 times 10 to the negative 21st power.
So really, like what I said with the positive one, you could really just count them and it's
Not well. Depends if by counting them, if your number would have already been negative. So if you would already think about your number as negative, yes. But if you're talking about the whole zeros rule, if you have count all the zeros, then give yourself 1 more and then make that number negative. Now here's the thing about using these negative powers up here. What did a negative power tell us to do in our exponents chapter? G? Write the reciprocal and then keep the power on that number, right? So 10 to the negative 21st is really 1 over 10 to the 21st. So that would be like 1, like trillion. I mean, something bigger than that. It'd actually be like 1, probably like quintillionth if each million has 6 zeros. So we have to figure out which one has 20 or 21. But yeah, so it'd be a really, really, really small fraction. That's why we use the negative exponents to shift it left or make my number smaller, because it's essentially just making fractions. 1/10, 100th, 1,000th, whatever the power is, takes us smaller and smaller and smaller. Yeah.
What if the number was negative, like negative 0.0000?
The number just stays negative. So the base being negative does not affect the power being negative. They don't really relate to each other. This would just, if that was negative, then my end result, like in standard notation, would be a negative number. So key concept is probably going to restate what we've pretty much said. Was there
When you are working with small numbers in standard form, it is helpful to express them in scientific notation. Method 1 for expressing 234 millionths in scientific notation.
So,
Move the decimal point to get a factor greater than or equal to 1, but less than 10.
Their process that they take, you can go either direction. That's why we talked about Lily's method compared to my method. They're both right. It depends on how
You end up with the decimal between the 2 and the 3. Write the number as a product of two factors.
And then we see that there's 3 zeros and the 2, so that was 4 spaces. Well, then when I write it,
234 millionths equals 2 and 34 hundredths times 1/10,000th. Write 1/10,000th as a power of 10. 1/10,000th equals 10 to the negative 4th power. 234 millionths equals 2 and 34 hundredths times 10 to the negative 4th power.
That's why we then change and use things. Actually, let me capture that.
Instead, power.
Method 2. Come on. Count the spaces individually. We say, okay, since I will have to take it left, my power is negative. How many spaces? 4. We do that again, except now we're going to convert them back to standard notation. So we take 1.32 times 10 to the negative 3rd. We're going to evaluate 10 to the negative 3rd actually represents 1,000th. So then I take 1.32 times 1,000th. I get that. I just realized I did not capture this guy. Capture this. And the last one, which is the way that we most normally take. We just let the power tell us what to do, and we follow the power. Questions? Didn't figure. I think we'll be able to get through this lesson pretty quick. So, your eyes. And actually, I was watching, anyone watch Brain Games? Yeah, I was watching Brain Games last night.
So was I.
So, what's interesting about your eyes is all idea of color is just what your brain has made up. So, what I see as blue, you might see completely differently, but we both think it's blue because we've been told that's blue. So, they talked about a green leaf is not actually green. It is because it reflects the color green. It absorbs all other spectrum of light. The only light that doesn't get absorbed is that green spectrum. That's why your eyes think it's green. So we're saying essentially something that's green is any color but green. Something that's red is all colors except for red. So it's this really crazy idea of color and how your brain perceives it. But coming back from that, digressing a little bit, really what we care about is that light is in waves. Depending on the color of light will depend on the frequency of the wave. Now frequency is how fast it like oscillates. So it might be a long wave, slower, or it might be a really fast wave. And that depends on how your eyes perceive it. So the ultra, or the violet, sorry, not ultraviolet, just violet. So the color violet, its wavelength is 0.000004 meters. Now, of course, they're measuring in meters because we want really small numbers, but we want to write this in scientific notation. So what's going to be the first term in there, Grace? What's the number that I use times 10 to a power? 4, because that's the only number I have. Now, I could put 4.0 if I want. I like using the decimal just to show that's where it is. If you only put 4, yeah, it's the same. It's just not written quite as accurately. She?
Would it be 4.0 to the 10 to the -7?
Well, let's check. I have, like, once I put my decimal here, I need to come back to get to where it actually, like, lives. 1, 2, 3, 4, 5, 6, 7. So you are absolutely right. It would be to the -7. The other thing we could do is count how many zeros or how many places does it have to go. So there's 1, 2, 3, 4, 5, 6, 7, counting the 4, because it has to cover that whole span. It goes from here to there. So try this on your own. X-rays wavelengths are 0.0000001 meters. Maybe go like 10 seconds. Riley, what do you think?
It said 1 times 10 to the -8th power.
Agree or disagree?
I agree.
Agree. I'm going to check it. 1, 2, 3, 4, 5, 6, 7, 8 would get me back to where I want to be. Absolutely correct. And the last got it. So, a nanometer is 1/100000th of a meter. Which unit, meters, nanometers, would be more appropriate for measuring wavelength of light? So, if a nanometer is 1/100000th, well, let's write, what is 1,000,000,000? Well, tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths, 10 millionths, 100 millionths, billionths. So there we go. So that is billionths place. So it'd be 1 in the billionths place. So here we have 1, 2, 3, 4, 5, 6, 7, 8 zeros. If I have 1, 2, 3, 4, 5, 6, 6 zeros here, 1, 2, 3, 4, 5, 6 zeros there.
Meters.
What if I did represent it in a nanometer? What would my number become? Is that like less than 1 or more than 1? Because since a nanometer is 1,000,000,000th, well, this is 4. What decimal place is that? Tenths, hundredths, thousandths, 10,000ths, 100,000ths, millionths. So that's 4 10,000,000ths. But that's bigger than a billion.
Oh yeah.
So the number would be bigger than 1 if we express it as a nanometer. So nanometer would make more sense because instead of using a decimal notation, we could actually use a whole number notation like 40 or 400 or 4,000, which we like better than using decimal notations. So being able to change your units can make the number much easier to deal with. So instead of saying we have 4 10,000,000ths of a meter, you'd probably say the 400 nanometers, I want to say.
when you move it, you add the 2 zeros.
Yeah, because we have to get to the billionths place to be the nanometer. Questions?
That's a one.
it's kind of like when we convert feet to inches. It's better to go to a smaller unit to get a bigger number because it makes life easier. It makes my numbers larger. So, Earth. We're all moving at a crazy fast speed right now. Everything beneath us is like liquid. And we all move kind of crazy. But one of the Earth's plates, and actually it's predicted that we're going to have a really big earthquake by, not us, but California. There's notes for today, and then there will be a video posted on Schoology too. California supposedly is going to have a really big earthquake by 2018. You know San Andreas, like the movie?
Yeah.
So I was just reading an article online. I subscribe to a couple science websites because, hey, the math teacher likes science. So the San Andreas, does anyone know what San Andreas is?
It's a fault. It's a big.
It's a big fault line, right? It's one of the biggest fault lines in the world because it's between two giant tectonic plates that are always moving. So that's what creates your earthquakes. And based on how they say history repeats itself. Well, it really does. The Earth has been through cycles of hot and cold way before we ever existed, and it will keep doing it way after we're ever dead. So the fact that global warming's happening, that would happen on its own. The question is, are we contributing to it happening faster and worsening? So that's not an argument for today's class. My belief is yes. There's scientific evidence. So all that aside, we've got our plates. Earth's plates move about 1.23 times 10 to the negative 2 centimeters per day. Let's talk about what that actually is in standard form. So what does that power tell me to do? Seth, go home.
Yeah.
Yeah.
You didn't.
Pranav, what does that power tell me to do?
It tells you to move. It tells you to move the decimal over 2 spots to the left.
Yeah, move my decimal 2 places left. So I kind of like to write it out how it is first, and then do what it tells me. I move it left 1. To move it left again, I'm gonna have to put a 0, and it's gonna land right out there. So it's actually gonna be 0.0123 centimeters. The unit stays the same. All we did was apply the power. The power of 10 to the negative 2 told me move your decimal 2 places left. Question or what? You keep
San Andreas thing or whatever.
I've not seen the movie. If you're
Alright,
gonna
I was
ask
gonna say,
about
is it gonna be that big?
I have no idea. I have not seen the movie. But most Hollywood movies are way exaggerated. What you normally worry about in earthquakes is buildings falling over. Because and now a lot of buildings built in locations where it's earthquake prone are built with that design in mind. So there's buildings that have floating posts where it can move and the posts can move. And so if you go to Chicago, we go up in the Willis Tower. When you're up there, you can feel it moving. All tall buildings move. If you climb a tree high enough, you feel the tree moving. Well, that's nature. Sure, it has to. It's wood. It bends. No, steel and concrete buildings move all the time, constantly moving. So you go out in the glass room where you can look straight down,
That's terrifying.
and you literally move it messes with your head. Yeah.
My little sister and my dad, my dad took my sister, Campbell, and I to New York,
Mm-hmm.
but since Riley had already been, they went to Chicago.
Mm.
We have pictures of how scared her face was when it was shaking. It was really
There was a girl who would not go out there, and so then we were about to leave, and she's like, "Wait, I want to go out there now!" She finally worked up the courage, real quick.
Have you been to the One World Trade Center?
No, not since they.
That is freaky.
Yeah.
If you go to the top, that's you can it's more than just.
I have been to the CN Tower in Toronto though,
I
and it's not like a room. They just have a glass floor. It's just part of the upper part of the tower. Because you go up in the center, and then the tower's bigger, so you walk around beyond where the elevators and stuff are. Chief?
And so the Washington Monument.
Yeah.
So there's an elevator to the top of
Right.
the monument. My sister got sick up there because she
Oh,
said
gross.
because she said she thought the thing was gonna tip over.
Yeah,
It looks like it's
concrete will move a little less than like skyscrapers where they're steel because metal can actually bend a little bit. So, but yeah, it would still probably move.
For that Toronto tower thing.
Yeah.
Whatever, I heard it's possible like where you can like hang on the edge of it or whatever.
I'm not
They,
certain.
Like clip like you to a
Oh,
harness,
okay,
like,
yeah.
You can lean off to the back. Did
Yeah.
you do that?
That's a
No.
place in
I was in 7th grade. We went for. I was in this like pull-out class called Sequoia. Kind of like we didn't have EPP back when I was in school, at least in Coshocton. So that was like our once a week. We'd kind of pull out and go do like EPP sort of stuff.
When I went to the CN Tower, like I laid down like on the floor,
Mm-hmm.
but that one's like 5 years old, so like I lived 24 hours.
Right, it's like it doesn't matter. All right, red blood cells, and this gets really interesting when you start comparing cell size. And in science, you're going to talk more about this. I was actually tutoring a student last night talking about chemical bonds, how things come together, and how that kind of relates to your body. So a red blood cell, 7.0 times 10 to the negative 6. I'm going to rewrite this because it's kind of hard to see. If I start with the right number, 7.0 times 10 to the negative 6. So when I look at my power of negative 6, I know it tells me to move my decimal left because it's negative, 6 places because it's a 6. So we apply that, move 1. Now here's one trick. Because moving 1 space got me to the end of my 7, can anyone like give me a shortcut for how to know how to write my number? Nate?
Wouldn't you just put, like, you subtract 1 by 6 and then put that amount of zeros?
So how many zeros? Yeah, so there's going to be 5 zeros because I went 1 place. I need to go a total of 6 places. So you know you need to go 5 more places. There's going to be 5 more zeros. So you can just put 1, 2, 3, 4, 5. Your decimal point out there. So this is actually going to become, when we write it in standard form, 0.000007 meters. Your red blood cells are very, very small. Now, because of the different sizes in blood cells, there's lots of cool technology that they do, because when you spin things, heavier things will go to the bottom and lighter things will go to the top. So when I go donate blood, they take out my blood, they put it in a machine, it spins it, separates out the red blood cells from the plasma, and then and the platelets, like it separates it all kinds of ways, and then they put the plasma back in. Because the different sizes, the different masses of the cells, they can literally just separate them like instantly. So I sit there, I watch it happen. It's kind of crazy. It takes about an hour.
And then they put plasma.
They put your plasma back in with some extra stuff added to it so it doesn't like coagulate or anything. But it like start to kind of like clot. But it's so you don't feel as bad. Like when you donate whole blood, they say like you're gonna feel kind of like, you just donated like a pint of blood. You're kind of low on blood. When I donate double red, I've given all my red blood cells, but my blood level is not as low because my plasma is still in my veins flowing. My body just needs to generate more red cells. So like I feel fine. Like I went and played disc golf after I donated blood one day. Like so I like doing that better. And they can make, then in the lab, they can take my 1 donation and make 3 pints out of it, as opposed to donating once and having 1 pint. So my donation really ends up giving them like 3 times the amount of blood. But they call it double red because they take twice as many blood cells. If that makes sense.
And then they put the protein. So they take one, then they usually do, but then they take
The only thing you can't make in a lab is the red cells. You can make all the other parts of the blood in a lab. So that's why they need the red cells. So we have our scientist here, right? I forget what his name is. I always think he's kind of like, a Dr. Evil sort of guy. So here's our other cells.
This is the
So
best
we
one
wanna
yet.
Talk about the comparison between the cells. So we've got our red blood cell, which now they've given us a tiny bit different. Instead of being 7, we've got an 8 now, because depending on the size, there will be slight variations in the red blood cell size. Then we've got white blood cell and cheek cells, so your actual like tissue cells. If you were to just make a hypothesis, what do you think is going to be bigger? Like, forget the numbers for a second. Do you think a tissue cell or a blood cell would be larger? Tissue, probably, right? Because It's like, and now you can physically look at a red cell, but it's much easier to like physically look at tissue cells. So let's compare that. So let's write all of these in scientific notation then. So it says estimate each number in scientific notation. That's probably going to come into play down here. My red cell, that's pretty easy to write in scientific notation. Be 8 times 10. Well, how far would the decimal have to move? 1, 2, 3, 4, 5, 6. We should have already kind of known that because of our last slide. 8 times 10 to the negative 6. Now if I write white blood cells, I'm going to change the color here. We're going to have, now what's the first number that I use? It comes before the times 10. Yeah. 1.08, or right about 1, times 10 to the, well now if my decimal's here, I need to move 1, 2, 3, 4, 5. So 10 to the negative 5th. Now wait. Now I've got different powers. When we're dealing with negative powers, right now, based off the power and the power alone, which is bigger? Something with 10 to the negative 6th or something with 10 to the negative 5th? Nate, you went first.
Well, Nate, it would be the white blood cell because, well, first of all, there's less negative numbers, so that means it's closer to 0.
Yeah.
It's closer
Well,
to positive numbers.
It's already positive, so you're kind of getting a little. So my power is closer to 0.
Yeah.
When you say it's closer to 0, it's hard to understand. So when your power is closer to 0, your number is bigger. Your like value of, so this is a bigger value, even though 8 compared to 1, well obviously my 8 is bigger, but because that goes 10 to the negative 6, and my white blood cell has 10 to the negative 5th, 10 to the negative 5th is going to be bigger. So when we look at a blank cell is about 6 times as large as the white cell. Well, if white cell is bigger than red cell, let's figure out about the cheek cell. So, it's not going to scroll my ink. The cheek cell, what would be my first number there, Olivia? The number that comes before the times 10?
Right. 63.
Ooh, 63?
6.3.
6.3, because it has to be, actually I'm just going to write on top of this, 6.3. It has to be a number greater than 1, less than 10. So 6.3 times, we'll now see how far your decimal has to go. If it's there now, 1, 2, 3, 4, 5. So it's 10 to the negative 5th. Now wait a minute, the powers now are the same. I have 10 to the negative 5th and 10 to the negative 5th. Since the powers are the same, Peyton?
Then it's the numbers.
Then we compare the numbers, 6.3, 1.08. So the cheek cell compared to the white cell, which is bigger?
The white or cheek cell.
The cheek cell, because the powers are the same. So we compare the base values, the 6.3 to the 1.8. So A is actually that the cheek cell.
You also couldn't say the white blood cell is 6 times larger as the red blood cell. That just didn't work.
Yeah, right. So a cheek cell is about blank times as large as a red blood cell. So now,
Never mind.
no. A cheek cell is about blank times as large as a red blood cell. B.
Oh.
So,
okay.
since the power, when we compare 10 to the negative 6, and we just talked about this, compared to 10 to the negative 5th down here, we know that that gives us 10 times as big. So if I wanted to write this in the same power, it would really, and this is not proper scientific notation, but if I wanted to get this in 10 to the negative 5th, if I move this decimal over 1, I'll get rid of one of my powers. So then it would be 0.8 times 10 to the negative 5th. This is not proper scientific notation,
Not between
but
the
I can compare the numbers now. So now that they have the same powers, I can just compare the base, 0.8 compared to 6.3. So essentially you're comparing like 8 and 63 in a way.
Wait, are we allowed to do that on tests?
To compare values, yes. But so this I'm just using for comparison. Like, it's not standard form and it's not scientific notation, but it is a correct representation of the number. It's just not in a form that we like. But I only did that to make my powers of 10 match. So now we can essentially say 0.8 times what will get us to 63, or about 6.4. Yeah? So if I have 0.8 compared to 6.3, think about it as 8 to 63. So 8 times 8, right? 64. Since they said estimate, it's pretty much 8 times as big. Here's why I didn't leave the powers as they were. 10 to the negative 6 compared to 10 to the negative 5th, that gives me a 10 times bigger. But 6.3 is less than 8, so I know it's going to be almost 10 times bigger, but not quite. So that's why we get 8 times bigger. A blank cell is about 1.25 times as large as a blank cell. So there's no power of 10 here. It's just a little over 1.25. What do you think? What would make sense? Zach?
A cheek cell is about no. A red blood cell is about 1 point. No. A white blood cell is about 1.25 times as large as a red blood cell.
There it is. We talked first. One of the first things we did as we looked at the comparison is that white was bigger than red, but not by that much. It's like comparing 8 and 10. Because if I made these powers the same, if I took this decimal and bumped it over 1, just like I did up here, but I went to the left, so I decreased my power, it got closer to 0. If I go to the right, it increases my power, so that would be 10.8 times 10 to the negative 6. Now my powers are the same, negative 6 and negative 6, so I could just compare 8 to 10, or almost 11, and that's how I get 1.25. Questions on this? The comparison, you just got to be careful with the comparison. The questions won't necessarily be as hard as this, but you do have to analyze, and so I forget if this is on your notes.
The questions were really easy.
On the homework?
Yeah.
So let's try got it. Length of cell A is 3 times 10 to the 4th. Length of cell B is 3 times 10 to the negative 5th. Sorry, I think I said 10 to the 4th. It's 10 to the negative 4th. How many times as long is cell A than cell B? So guys, here's where I'm going to use that trick. And this is kind of hard. So when I have, let's back up. Forget about this question for a second. When we have 1,234 times 10 to the 0. It's in standard form right now. So this 10 to the 0 is really 1. It does nothing. I want to put it in scientific notation. So I move my decimal left. I do this, right? Like I'm making this happen. I write 1.234 times 10. Now my power to get back to where it should be becomes 3. So when we move it left, my power gets bigger. So I would write in your notes, move decimal left, power increases, but be careful because when we work with negative values, increases would be gets closer to 0. I would also maybe write the inverse statement and say that when we move our decimal right, our power decreases. But remember, with negative exponents, decreases would be a bigger negative number. It'd be further away from
Wait,
0.
both of those for negative numbers?
For negative or positive powers, it does the same regardless of what your power of 10 is. So that's when I physically move. And why I'm telling you that is it will be much easier to compare these values if I have the same power. Now we know, because we just talked about it, anything closer to 0, the power being closer to 0 when we're dealing with negatives, like which of these is bigger, cell A or cell B? A, because its power is closer to 0. It will take it like less of a distance left. Another way I can compare this is just move my decimal to make the powers match. So I want to make this power, let's just say I want to make that decrease. I want to make it go to 10 to the negative 5th. So to do that, to make the power decrease, I move the decimal right. So this would really be 30 times 10 to the negative 5th. My powers now match. And I see 30 compared to 3 is 10 times as large. The other way you could do it is write them both in standard notation and compare them. But because I know what's coming on the homework, like not just tonight's, but like in the future, that's a good rule to have tucked away, is that when we move the decimal, what does it do to the power? Well, I mean, that we talked about what it does. Just saying like that rule, having that. And if you can't remember it, say you're on a test or something, just set up a problem, like set up a number, and then see what happens. Like set up 1,234, put it in scientific notation, see what happens there. I'm going to go ahead and wrap us up a couple minutes early so my tech gurus can help me if the video's goofed up. Help me figure that out.